Well, let me tell you something strange. You weigh something. Right now, sitting there, you have mass. Your body has mass. The chair beneath you has mass. The atoms in your fingertips, the molecules in the air, the particles in every object you can see, they all have mass. And that seems obvious, natural, like asking why water is wet. But here's the thing, nobody knew why. For decades, the best physics we had, the standard model, the most successful theory ever created, predicted that every particle should be massless. Every single one. Zero mass. Which would mean you should not exist. Atoms should not exist. Nothing should exist except light racing through empty space forever. But you do exist. So something had to give particles mass. And the answer to that question, the solution to why anything weighs anything at all, is one of the most beautiful stories in all of physics. Now, before we get into what gives particles mass, let me tell you what the problem was. Because understanding the problem is half the battle here. You see, the standard model is built on something called gauge symmetry. Very elegant mathematics. There are three forces described by the standard model: electromagnetism, the weak nuclear force, and the strong nuclear force. Each has its own symmetry. U1 for electromagnetism, SU2 for the weak force, SU3 for the strong force. Beautiful equations. And these symmetries are not just mathematical decoration, they are fundamental. The entire theory depends on them. The equations only work if these symmetries hold. But here is the problem. Gauge symmetry forbids mass. If you try to write down a mass term for a gauge boson, say the W boson that mediates the weak force, you violate the symmetry. The equations break. They stop making sense. It is like trying to put a square peg in a round hole. The mathematics will not allow it. So the standard model, in its pure form, with perfect gauge symmetry, predicts that all gauge bosons should be massless. All of them. The photon, the W boson, the Z boson, the gluons. Zero mass for everyone. And for photons and gluons, this is fine. They are massless. They travel at the speed of light. No problem there. But the W and Z bosons, the particles that carry the weak nuclear force, are not massless. We measured them decades before we understood why they had mass. The W boson weighs about 80 times what a proton weighs. The Z boson weighs about 91 times the proton mass. These are heavy particles, very heavy for fundamental particles. So we had a contradiction. The theory said they should be massless, reality said they were not. Something had to resolve this. Now, there is a deeper issue here too. Electromagnetism and the weak force at high energies are actually the same force, the electroweak force. This was figured out in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg. At very high temperatures, like those just after the Big Bang, these two forces are unified. One force, not two. But at low energies, the energies we experience every day, they look completely different. Electromagnetism has infinite range. Photons are massless. The weak force has incredibly short range, about 1,000th the diameter of a proton. W and Z bosons are massive. How do you go from one unified force to two distinct forces with completely different properties? You need to break the symmetry somehow. But you cannot just break it arbitrarily. You need a mechanism that preserves the gauge invariance mathematically while still allowing the particles to have mass. This is called spontaneous symmetry breaking. And this is where the story gets interesting. In 1964, several physicists independently came up with the answer. Peter Higgs in the UK, François Englert and Robert Brout in Belgium, and a few others. They all realized the same thing around the same time, which is how physics often works. Good ideas are in the air, and several people grab them at once. What they proposed was this. Suppose there is a field that fills all of space, that has a non-zero value even in the vacuum, even in empty space, not zero. A field that is always on, everywhere, at all times. And suppose particles interact with this field. The strength of the interaction determines the particle's mass. Particles that interact strongly with the field gain a lot of mass. Particles that interact weakly gain a little mass. Particles that do not interact at all remain massless. This field, they said, is what gives particles mass. We call it the Higgs field. Now let me explain how this works, because it is really quite beautiful. Imagine you are at a party, a crowded party. You are trying to walk across the room. If you are nobody special, you can walk right through the crowd. People step aside. You move freely, low resistance. But suppose you are a celebrity. Everybody wants to talk to you. People cluster around you, you get slowed down. High resistance. The more famous you are, the more people mob you, the harder it is to move. That resistance to motion, that difficulty in accelerating, is like mass. Mass is resistance to acceleration. The Higgs field is the crowd. Particles are the people moving through it. Photons do not interact with the Higgs field. They are the nobody. They pass through unimpeded. Zero mass. They travel at the speed of light. Electrons interact weakly with the Higgs field. They gain a small mass, about 9.11 times 10 to the minus 31 kilograms. W and Z bosons interact strongly. They gain large masses. Top quarks, the heaviest elementary particles we know, interact very strongly with the Higgs field. They are the celebrity getting mobbed. Their mass is about 173 giga-electron volts, which is about 184 times the proton mass. Enormous for a fundamental particle. Now, the analogy is not perfect. Nothing is pushing against particles as they move. There is no friction. But the idea captures something true. Mass is resistance to acceleration caused by interaction with a background field. Without the Higgs field, all particles would be massless. They would all travel at the speed of light. There would be no atoms, no chemistry, no structure, no you. The Higgs field is what makes the material world possible. But here is the thing. If the Higgs field exists, it should have excitations, ripples in the field. Just like the electromagnetic field has photons, the Higgs field should have a particle. We call it the Higgs boson. It is the quantum of the Higgs field. And if the theory is right, we should be able to detect it. We should be able to create it in a particle accelerator. Smash protons together at high enough energy, and sometimes, rarely, a Higgs boson should appear. Then it should decay almost immediately into other particles. Photons, W bosons, Z bosons, bottom quarks. The decay product should have a specific pattern, a specific signature. Find that pattern, and you have found the Higgs. So that is what physicists set out to do. The problem was, the theory did not predict the mass of the Higgs boson. It could be anywhere from a few giga-electron volts to hundreds of giga-electron volts. You had to search for it. And to create a particle that heavy, you need enormous energy. You need the most powerful particle accelerator ever built. Enter the Large Hadron Collider at CERN, on the border between France and Switzerland, a ring 27 kilometers around. Two beams of protons circling in opposite directions accelerated to 99.9999%, the speed of light, then smashed together. Collision energy up to 13 trillion electron volts. Trillions of collisions every second. Two enormous detectors, ATLAS and CMS, watching for the decay products of particles created in those collisions. The LHC turned on in 2008. Then it had to be shut down for repairs after an accident. It came back online in 2009. By 2010, it was running at 7 tera electron volts collision energy. By 2011, it was running at higher energies, and the data was piling up. Physicists were looking for a bump in the data, a slight excess of events at a particular mass. That bump would be the Higgs boson. They saw hints, tantalizing hints, but not enough to be sure. They kept collecting data, more collisions, more decays, more statistics. And then, on July 4, 2012, CERN held a press conference. They announced the discovery of a new particle, mass around 125 giga-electron volts, decaying into photons, Z bosons, W bosons, bottom quarks, tau leptons. The properties matched the predictions for the Higgs boson. The statistical significance was 5 sigma. That means the probability of this being a random fluke is about 1 in 3.5 million. In particle physics, 5 sigma is the gold standard. It means discovery. Both Atlas and CMS saw it independently. Same mass, same properties. It was the Higgs boson. Nearly 50 years after the theory was proposed, the particle was found. Peter Higgs was in the audience at CERN that day. He cried. In October 2013, Peter Higgs and François Englert were awarded the Nobel Prize in Physics. Robert Brute had passed away in 2011, and Nobel Prizes are not awarded posthumously. But his contribution was acknowledged. The discovery validated the mechanism. The Higgs field exists. It fills all of space. It gives particles their masses. The Standard Model was complete, or so it seemed. But here is where things get complicated. Because the Higgs field explains how particles get mass, but it does not explain why the Higgs field itself has the value it does. The Higgs field has what is called a vacuum expectation value. In empty space, far from any particles, the Higgs field has a non-zero value. That value is about 246 giga-electron volts. Why 246? Why not 0? Why not a million? We do not know. It is a free parameter in the Standard Model. We measure it, but the theory does not predict it. We put it in by hand, and this matters. Because if the Higgs field had a different value, the masses of all particles would be different. If it was 0, all particles would be massless. No atoms, no stars, no life. If it were much higher, all particles would be incredibly heavy. Chemistry would not work. Nuclear reactions in stars would not work. Again, no life. The value of the Higgs field has to be in a very narrow range for the universe to be even remotely like what we see. And we do not know why it is in that range. It just is. Even more puzzling is the mass of the Higgs boson itself. The Higgs boson weighs 125 giga-electron volts, but quantum mechanics says it should not weigh that. You see, in quantum field theory, particles interact with virtual particles, electrons interact with virtual photons, quarks interact with virtual gluons, and the Higgs boson interacts with everything, every particle, top quarks, W bosons, Z bosons, everything in the Standard Model. These interactions contribute to the Higgs boson's mass through quantum corrections. And when you calculate those corrections, you get an absurd answer. The corrections should drive the Higgs mass either to 0 or to the Planck scale, which is about 10 to the 19th giga-electron volts. That is 100 million trillion times heavier than what we observe. To keep the Higgs mass at 125 giga-electron volts, you have to fine-tune the parameters of the theory to incredible precision. 1 part in 10 to the 34. That is like balancing a pencil on its tip, but the tip is a trillion times sharper. This is called the hierarchy problem. Why is the Higgs mass so much lighter than the Planck scale? Why does the fine-tuning work out so perfectly? We do not know. Most physicists think this means there is new physics beyond the Standard Model. Something we have not discovered yet, maybe supersymmetry, which predicts a partner particle for every Standard Model particle. The partner particles would contribute quantum corrections that cancel out the huge corrections from Standard Model particles. But we have not found any supersymmetric particles. The LHC has looked. Nothing yet. Maybe extra dimensions. Maybe something else entirely. Nobody knows. Now let me tell you something else. The Higgs mechanism explains the masses of elementary particles. Electrons, quarks, W bosons, Z bosons. But those particles contribute only about 1% of your mass. Where does the other 99% come from? It comes from the binding energy of quarks inside protons and neutrons. You see, protons and neutrons are not elementary particles. They are made of quarks held together by gluons. Gluons are the particles that carry the strong nuclear force. And gluons are massless. But the energy of the gluon fields inside a proton has mass. E equals mc squared works both ways. Energy has mass. Most of the mass of a proton is not the mass of the quarks. It is the energy of the gluon field. The quarks are zipping around inside the proton at nearly the speed of light, and the gluons are holding them in. That binding energy, that kinetic energy, that is where most of your mass comes from. So the Higgs field gives the elementary particles their masses. but the strong nuclear force gives you most of yours. The Higgs gets the credit, but the strong force does most of the work. And neither of them explains why mass gravitates. Why does mass curve spacetime? Why does mass attract other mass? That is gravity. That is general relativity. And we have not unified general relativity with quantum mechanics. We do not have a quantum theory of gravity. So even with the Higgs, even knowing how particles get mass, we do not know why mass does what it does. We know the mechanism, but not the meaning. Think about that. We have found the field that gives particles mass. We have detected the Higgs boson. We have measured its properties. We know it exists, but we do not know why it exists. We do not know why it has the value it has. We do not know why the Higgs boson has the mass it has. We do not know what sets the parameters. The Higgs field is, in some sense, a band-aid. It fixes the mass problem, but it does not explain the deeper question. Why mass? Why this amount of mass and not some other amount? Why is the electron mass about 9 times 10 to the minus 31 kilograms and not 10 times that or 100th of that? And here is something that should bother you. The Higgs field is everywhere. It fills all of space. You are swimming in it right now. It is not some distant theoretical construct. It is here. It is interacting with every particle in your body, every electron, every quark. The resistance you feel when you try to move is partly the Higgs field. And yet you cannot feel it directly. You cannot turn it off. You cannot measure it locally. The only way we know it exists is by smashing particles together at absurd energies and watching for decay products. The Higgs field is the most intimate part of reality, and it is completely invisible to us. Now, let me tell you what I think is beautiful about this. The Standard Model predicted that particles should be massless. Reality disagreed. So physicists invented a field, the Higgs field, that would fix the problem. And then, 50 years later, they went and found it. They built the most complex machine ever built. They smashed trillions of particles together. They sifted through mountains of data. And they found exactly what the theory predicted. A particle with mass around 125 giga-electron-volts decaying in the ways predicted with the properties predicted. That is extraordinary. That is science working. You have a problem. You propose a solution. You test the solution. And sometimes, against all odds, the solution is correct. The universe did not have to work this way. But it does. But the story is not over. Because the Higgs discovery answered one question and opened a dozen more. Why does the Higgs field exist? Why does it have the value it has? Why is the Higgs boson so light compared to the Planck scale? What is the new physics that solved the hierarchy problem? Is there a deeper theory that explains the Standard Model parameters? We do not know, not yet. But we keep looking. That is what physicists do. You solve one mystery, and another one appears. You peel back one layer, and there is another layer underneath. And maybe, someday, we will understand why the Higgs field exists. Maybe we will find the theory that predicts its value. Maybe we will unify gravity with quantum mechanics and understand why mass curves space-time. Or maybe we will find that the Higgs field is not fundamental either. Maybe it is made of something deeper, something we have not imagined yet. That is how physics works. Every answer reveals new questions. Every solved mystery points to a deeper mystery. But here's what we know right now. We know that particles have mass because they interact with the Higgs field. We know the Higgs field exists because we detected the Higgs boson. We know the Higgs boson weighs 125 giga-electron volts because we measured it. We know these things. And that is remarkable. 50 years ago, we did not know why particles had mass. Now we do. We have not answered all the questions. We have not solved all the mysteries. But we have answered this one. And that, I think, is beautiful. You are made of particles. Those particles have mass because of the Higgs field. Without the Higgs field, you would not exist. Atoms would not exist. Stars would not exist. The universe would be nothing but light racing through empty space forever. But the Higgs field is there. It has been there since a fraction of a second after the Big Bang. And because it is there, particles have mass. Atoms form. Stars ignite. planets condense, life emerges. And here we are, made of particles that got their mass from a field that fills all of space, trying to understand how it all works. That is the story of the Higgs field, the story of why anything has mass, the story of how physicists solved one of the deepest problems in all of physics. It is not the end of the story. There are more chapters to come. But this chapter, this discovery, this moment when we found the Higgs boson and confirmed the mechanism that gives particles mass, this is one of the great triumphs of human curiosity. We asked a question: why do particles have mass? And we found the answer. Not the complete answer, not the final answer, but an answer. A real, testable, confirmed answer. And that is what science is: asking questions, finding answers, and then asking deeper questions. Nobody knows what comes next. Maybe we will find supersymmetric particles. Maybe we will discover extra dimensions. Maybe we will find that the Higgs field is not fundamental. Or maybe the standard model is all there is, and the Higgs field is just a brute fact of reality, unexplained and unexplainable. We do not know. But we keep looking. We keep asking. We keep building bigger accelerators and better detectors. We keep smashing particles together and watching what happens. Because that is what we do. We are curious. We want to know. And sometimes, if we are very lucky and very persistent, the universe tells us its secrets. And that is the Higgs field. That is why anything has mass. That is how we know. That is science.